Swayam Prabha. Digital India. Educated India.
Hello viewers, in the last class we saw that what are the various terminology related to machine foundations, and then we saw that how you can analyze linear spring soil system. Then we saw what exactly do we mean by free vibration, force vibration, and how the analysis can be carried out with and without damping. We saw in the last class also that there were three type of foundation. One was block, then box, and then wall foundation. So within the scope of your course we have this block foundation. So let us try to see that how you can analyze this block foundation. What exactly are the methodologies adopted for this analysis? So we will discuss now the method of analysis of a block foundation. Basically, there are two methods for the analysis of this machine foundation. First one is method based on linear elastic weightless spring, that you have already seen that how you can represent the system by spring and mass system. Then method based on linear theory of elasticity, that is elastic half space. So first let us try to see that how this method based on linear elastic weightless spring works. In this method the soil is replaced by elastic springs. See, anything that if you want to have its response, you have to convert into some mathematical form so that you can get its response. So in that case, as such soil you cannot it is natural occurring soil, natural occurring material. So we really need to replace it such that we can convert this natural occurring soil to some kind of model. So for modeling the soil, the elastic springs are used. Equation for natural frequencies can be written and compared with operating frequency. You have already seen that when we were discussing about this soil, this spring mass system, in that one you have seen that how you can get the equation for natural frequency and how you can compare that with operating frequency using that frequency ratio R, which was the ratio of operating frequency of machine and the natural frequency, and the standard curves with respect to, that is frequency ratio versus magnification factor, have been given for zero damping as well as with damping. So from there we can get this natural frequencies. To avoid resonance, the frequency ratio should be either less than 0.5 or greater than 1.5. We have seen that exactly the resonance condition occurs at exactly frequency ratio to be equal to 1. However, in the vicinity of R is equal to 1 also the amplitude values are quite high. So that is why to avoid any kind of resonance, the frequency ratio is kept in the range of 0.5 and 1.5. The influence of damping can be introduced in the solution of equations, that we have already seen that how it has been introduced. That effect of damping on amplitude computed at operating frequency is small as compared to that as resonance. As I showed you the earlier figure, in that one we have seen that at resonance the amplitude is quite high, while at operating speed, that is when the frequency ratio are quite high, then the amplitude or the magnification factor was not that much, it was very small. So the amplitude is not that much at operating speed. The method is simple, though a proper evaluation of soil constants is rather difficult, since you are replacing the soil by equivalent spring. So, you need to know that what exactly is the characteristic of that particular soil, so that the modeling can be done properly. And to evaluate these soil constant, it is quite difficult. We have different measures. So, let us try to see that what are the different soil constants and how we can obtain them. So, first, soil spring constants. A spring constant is defined as a force causing a unit deformation. So, wherever I am using that spring constant, this picture should come into your mind that it is the force which will cause unit deformation. For the analysis of a block foundation, one of the approaches is to consider the soil as weightless elastic springs. So, since we are talking of the analysis of block foundation, so the soil is being modeled as weightless elastic springs, that a series of springs will be there. When the block foundation undergoes vertical oscillation, the compression is induced at the base of the footing. You have seen that the block foundation, it rests on the soil, and in case you are representing the soil by a set of springs, whenever this block foundation will be subjected to the load, it will be that machine foundation is there, so it will be subjected to static as well as dynamic load. With result of that, it will undergo some oscillation, and so with the consequence of this oscillation, this compression will be induced at the base of the footing. On the contrary, if the block undergoes translation about x or y axis, shear stresses are induced at the base of the foundation block. So, you see either the translation will be there in x or y direction. So, you see here I am considering z direction as the vertical direction, however, x and y directions are in horizontal planes. So, in case the force, because it is dynamic load, it can be vertical, it can be horizontal, from any direction it can come. So, if due to the presence of dynamic load, this block, if it is undergoing the translation, that is if the movement is taking place along x or y direction, or the movement is taking place in horizontal plane, then the shear stresses will be induced as compared to the compression which was there when it was subjected to the vertical load. Okay. So, two type of things are there. In one case, the compression at the base of the footing was induced, and in another case, in case when the block is undergoing translation about x and y axis, the shear stresses are induced at the base of the foundation block. The nature of equivalent spring stiffness will be different in each of the different modes of vibration. Obviously, when it is subjected to compression at the base of the footing, the property of the soil or the equivalent spring with which you have replaced the soil, it will be different, and in case the translation is taking place, then in that case the spring constant will be different. So, as x and y axes are interchangeable, there are basically 4 different types of equivalent soil spring constant which are of interest for the purpose of analysis. So, you see the number of mode of vibration, different number of mode of vibration, different will be the equivalent stiffness of the equivalent spring by which you are representing the soil. So, whatever is the mode of the vibration, one corresponding value of spring constant of the soil will be there. If it is compression, that spring constant will be different. If it is translation along x or y axis, it will be different. So, corresponding to the various mode of vibration, 4 different type of equivalent soil spring constants are there. Let us try to see one by one that what exactly are they, what is the physical meaning, physical interpretation of them, how you can determine them using different techniques. So, the first one is coefficient of elastic uniform compression, second is coefficient of elastic uniform shear, third is coefficient of elastic non-uniform shear, and the fourth is coefficient of elastic non-uniform compression. So these are basically 4 types of equivalent soil spring constants. First, let us see that coefficient of elastic uniform compression. We represent it as C subscript u, that is Cu. How we define it? As that it is the ratio of external uniform pressure to the elastic part of the settlement. Wherever we talk in terms of spring constant, you know that it is the force required to cause unit deformation. So that is what is there. This is also kind of spring constant. So it is the ratio of external uniform pressure to elastic part of the settlement. So when you divide it, that means that you are talking that force per unit deformation. So what is this force in this case? It is the external uniform pressure, and what is that settlement is the elastic part of the settlement. As we were discussing in case when we were discussing that pile foundation, then we have discussed that what is the elastic and plastic settlement. So in this case also you will have elastic settlement as well as the plastic settlement. So in case of elastic uniform compression coefficient, it is the ratio of external uniform pressure to the elastic part of the settlement. Then second one is coefficient of elastic uniform shear. We represent it as C tau. Tau is in subscript, and it is defined as that it is the ratio of average shear stress at the foundation contact area to the elastic part of displacement in sliding. See, it is not compressing right now. So it is the translation which is taking place either in x or y direction, or along x or y axes. So wherever there is translation, we have seen that there will be development of shear stress at the base of the footing. So in that case, if it is subjected to the translation along x or y axis, in that case this equivalent soil spring stiffness is defined as coefficient of elastic uniform shear, where it is the ratio of the average shear stress which is generated at foundation contact area to the elastic part of the displacement in sliding. In above case, it was elastic part of the settlement, that was a vertical compression. However, in this case it is the displacement in sliding. Third one is coefficient of elastic non-uniform shear. We represent it as C psi. It is the ratio of external moment applied to the vertical axis to the product of polar moment of inertia of contact area of base of foundation and angle of rotation of the foundation. You see, if the vertical x and y axes are horizontal axes and z axis is the vertical axis. If the external moment which is applied to the vertical axis, then in that case what will happen, you have the block area of the block foundation. So you can get the polar moment of inertia of the same, and then you take the ratio of that polar moment of the inertia to the angle of rotation of the foundation. You see that I told you that spring constant is the force to cause unit deformation or deflection. When the force is causing the deflection, that is in case of compression, you have seen that it will be the vertical compression. In case of the translation, it will be the displacement in sliding. However, if any system or any body is subjected to a moment, there will not be any translation, there will be rotational movement. So that is what is happening here, that it is subjected to external moment, and so the resulting deformation will not be the translation but the rotational one. So that angle of rotation of the foundation. So you have, while you find out the spring constant, equivalent spring constant, then you have to take the ratio of external moment which you are applying to the vertical stress to the product of polar moment of inertia of contact area of the base of foundation and the ratio with angle of rotation of the foundation. Then coefficient of elastic non-uniform compression. This is represented by C phi. Phi is in subscript. It is the ratio of external moment about a horizontal axis. See, in the third case it was about vertical axis to the product of moment of inertia of contact area of base of the foundation about the same axis and the corresponding angle of rotation of the foundation uniform pressure to the elastic part of the settlement. As it was there in case of this non-uniform shear, exactly in this case also it is subjected to external moment, but about horizontal axis. So, you have to take the ratio as per this particular definition to determine, to obtain the coefficient of elastic non-uniform compression. Now, how you can determine these spring constants? Let us try to see that how we can determine this equivalent soil spring constants. So, the soil spring constant can be estimated from several in situ and lab tests. In situ tests, they are conducted in field, however, lab tests obviously, as name suggests, they are conducted in laboratory. So, in situ tests are preferred because they represent the real situation which is exactly existing in the field, and which will be they will be representing the exact condition that the foundation or the soil foundation system will be subjected to. This IS code, that Indian Standard Code of Practice is there, and its number is 5249, that is IS 5249 1992, provides the details of tests for the determination of dynamic properties of soil. What are these tests? These tests are cyclic plate load test, then block vibration test, free vibration test, and wave propagation test. Let us try to see that what exactly are these tests, how they are conducted, what are the different guidelines given in IS code, and how you can analyze the test data to obtain or to estimate this equivalent soil spring constants. So, first we discuss about the cyclic plate load test. In this test, the magnitude of load is maintained constant till the settlement of the test plate is completed. As you see, as the name suggests, that it is cyclic, and since the dynamic loads are coming into picture, obviously you have to go for cyclic kind of loading. So, this is an in situ test conducted in the field. A plate is there, a foundation, a representative plate is there. So, wherever you have to conduct that particular test, you have to put the arrangement at that particular depth, and then the loading arrangement is made in such a manner that loading as well as unloading can take place. So, whenever you apply a load, you obviously on the application of that load, the soil beneath that plate will be deflecting, or the some settlement will be taking place. So, you have to give sufficient time that that particular settlement has been stabilized, it is not further settling. So, for that purpose, the magnitude of the load is to be maintained constant till the settlement of the test plate is complete. That means that whenever the further settlement of the test plate is not occurring, then only you can increase or decrease the load in case of loading or in case of unloading respectively, but till the point the test plate is settling, you have to maintain the load on the test plate. The load is then released to 0 and the plate allowed to rebound. So, first is once you have to load it to some particular load, then you have to unload it. So, after loading, let us say for the first cycle, after loading you have to maintain that load till the test plate stops settling. Then from that particular point of time, you have to go on withdrawing the load from the test plate. That means that you have to unload the test plate. So, in that particular process you will be removing the load in some steps. So, in that case the load will be released to 0, and obviously due to the sum of the elasticity which is present in the soil, the test plate will have the tendency to rebound. Although the settlement which has already occurred, the resulting settlement will not be 0, that is, it will not be recovering whole of the settlement, but some part of the settlement it will be recovering, and that part of the settlement is called as elastic settlement. So then when this test plate is allowed to rebound, you can note down that once this rebound is stopped, you can note down that particular reading of the test plate, that is that particular settlement. So that is there, that the reading of final settlement is taken. The load is then increased to next higher magnitude of loading and maintained constant till the settlement is complete, which again is recorded. So once you have loaded and then you unload it to 0, then further loading takes place, and exactly in the similar manner as you did for the first loading cycle, you have to do for the second loading cycle, that whatever is the maximum loading intensity on the test plate, corresponding to that obviously the plate is going to settle. So you have to maintain that much loading intensity till the time test plate stops settling. So till the point it is settling down, you have to maintain that particular load, and wherever that settlement stops, you have to note down that reading. Then the load is then further reduced to 0 and the settlement reading is taken, as it was done in case of first unloading cycle. From the second loading cycle, you go on withdrawing the load such that the load on the test plate becomes 0, and in this process you must allow the test plate to rebound, because whatever is the elastic settlement or due to elastic nature, it will have the tendency to rebound or to recover some of the settlement. So that particular settlement reading is also to be taken, and then further the next increment of the load is applied. Again this procedure is repeated. The cycles of loading, unloading and reloading are continued till the required final load is reached. So you see, either the final load is reached, this IS code has given the provision that what should be this final load till the plate fails. You can see you will be having one particular condition in some loading cycle, that the plate will not be taking any further load, or the failure will be represented by excessive settlement of the plate. So there, till that particular level, till the failure of the soil which is around the plate, you have to go on loading, unloading and then reloading again. From the load settlement data, a graph is plotted between load intensity P and elastic settlement SE. You see, whenever we were allowing the plate to rebound, to what extent it has rebound, we have noted down that final settlement. So from there we can get the elastic settlement, because whatever it has recovered, that is a part of the settlement which is elastic, remaining is plastic settlement. So the elastic settlement we can get corresponding to each loading intensity. The slope of the load intensity settlement data is the coefficient of elastic uniform compression. So from the load settlement data, directly you will be getting this load intensity P versus elastic settlement, and the slope of this particular curve will give you the coefficient of elastic uniform compression. So I hope that now you understood that how you can get the coefficient of elastic uniform compression using cyclic plate load test data. So here you see that Cu was the coefficient which we are intent to find out, is equal to P by Se, where P is the load intensity in kilonewton per meter square or kg force per centimeter square. Se is elastic rebound corresponding to P in meter or centimeter. Then your unit of Cu will be kilonewton per meter cube or kg force per centimeter cube. You have to be consistent as far as the units are concerned. If you are using this SI units, kilonewton per meter square and meter you should use, or in case of CGS you have to use this kg force per centimeter square and centimeter for elastic rebound. Now this was all about the cyclic plate load test. So cyclic plate load test gives us the coefficient of compression, that is elastic uniform compression, that is Cu. Now let us try to see that how this block vibration test is conducted. You remember that we talked of 4 tests. First was cyclic plate load test and the second is block vibration test. In this test, a concrete block of size 1.5 meter, 0.75 meter and 0.7 meter, which is the height of the block, is cast in a pit at a proposed depth of foundation. So wherever you are planning to place the foundation at that particular depth, you can create a pit till that particular depth, and there on that particular depth the concrete block which is of these dimension is casted. Then foundation bolts for fixing oscillator and motor assembly are embedded in the concrete block at the time of casting the block. So while you cast the block, the bolts, because you know that oscillator and the motor, they will be performing there because it is machine foundation. So you have to fix the bolt while you are constructing that particular block, so that subsequently you can fix oscillator and motor to this concrete block. The motor and oscillator assembly is mounted on the block. So we have the fixing arrangement, we have the bolts for that. So with the help of those bolts, the motor and the oscillator, they are fixed on the block. You can see here that it is the test pit. This is the figure which has been taken from IS 5249/1992. So this IS code, if it is available to you, you can directly get this particular figure from that IS code. So this is this shows the setup for block vibration test. As I told you that it is to be conducted in a test pit. You see, this is the test pit, that is at this particular depth from the ground surface you are planning to place the foundation for that particular machine. And here you see a CC block, that is concrete block, has been casted here, and on top of that this assembly of oscillator and motor has been mounted. However, these are to take the readings for this block vibration test that we will see right now. Then this is the block diagram for testing equipment for block vibration test. This is again has been taken from 5249/1992, that is IS code. It is this concrete block. So you can have a look that how it looks from the top. So this is the concrete block. On top of that, this is the motor and oscillator which has been mounted. Here is the amplifier. Here is the power supply. This is speed controller unit. So and here it is transducer to take the reading. How it is done, that there are two types of tests, that is one is vertical vibration test, another is horizontal vibration test. So what exactly these tests are and what are their salient features, we will see one by one. That first let us see that vertical vibration test. The mechanical oscillator is mounted on the block such that it generates purely vertical sinusoidal vibrations, and the line of action of vibratory force passes through the CG of the block, that is center of gravity of the block. As the name of the test suggests that it is vertical vibration test. So the mechanical oscillator which has been mounted on the concrete block, it is mounted in such a manner that it generates the oscillation in vertical direction, that is vertical sinusoidal vibration, and its line of action, that is it will be creating the external force which will be acting on that particular block. So you see, as the name suggests, that is vertical vibration test, the mechanical oscillator is mounted on the block such that it generates purely vertical sinusoidal vibration. So in case of vertical vibration test, which the whatever is the oscillation which is getting generated, that has to be essentially vertical sinusoidal vibration, and the line of action of vibratory force passes through the center of gravity of the block. So the whatever is this mechanical oscillator which has been mounted, we have to make sure with the help of these calibrated transducers that it is generating purely vertical sinusoidal vibration, and this particular line of action of this external force must coincide with the center of gravity of the concrete block on which this oscillator has been mounted. Then two acceleration pickups duly calibrated are mounted on the block such that they sense vertical motion of the block. So to note down or to have the knowledge that what exactly is the vertical motion of the block, how it is taking place, these acceleration pickups are also mounted on the block. Choosing a suitable value of angle of setting of eccentric masses, the oscillator is made to run at a constant frequency. So little eccentricity of the masses is there. So for that particular value of angle of setting of eccentricity masses, the oscillator has to run at a constant frequency. For one particular eccentricity, the frequency of the oscillator should not be different. The signals of acceleration pickups are recorded through amplifiers and pen recorded or any other suitable recording indicating devices. So the signals of acceleration, then after that it is being converted, that is first the test is conducted, whatever is the data that you collect, and then you have to analyze. So for that the signal of the acceleration pickups are recorded through amplifiers or pen recorded or any other suitable device. So how they are being analyzed afterwards, we will see here. The frequency of the oscillator is then increased and the process is repeated. So you see, first for one constant frequency the experiment was conducted, and then this frequency was increased and the whole experiment was repeated again. So the same process is continued for other eccentricity setting. So you pick different eccentricity setting and choose a particular constant frequency throughout that, and then you go on conducting the test and go on recording the response of acceleration pickups. In a forced vertical vibration test, the amplitude of vibration, that is Az, at a given frequency Fz is given by Az is equal to small az divided by 4 pi square Fz, where this Az is acceleration in the vertical direction. You see, you were recording the response of acceleration pickups. That is how you will be able to get this acceleration in the vertical direction. Then amplitude, then once you know this Az, you can get this amplitude. How? Amplitude versus frequency curve is then plotted for each eccentricity value to obtain the natural frequency of soil block system. We will see with the help of one figure that how it is obtained, but from this particular expression, once this Az is known and at a given frequency, so this is also given. So this you are measuring from the response of acceleration pickups. So once this and this they are known, Az can be known, and then this amplitude Az versus frequency is known, can be plotted for corresponding eccentricity values. So the coefficient of elastic uniform compression using this vertical vibration test can be obtained as 4 pi square F nz square m by A. Now you see here that you have plotted amplitude versus frequency curve. This is for one typical eccentricity value. So that is why here I am writing as typical amplitude versus frequency curve. So for one particular eccentricity value, you can get this amplitude for corresponding different frequency. So what will happen when the frequency is less? First it will go on increasing and then it will attain a peak value, and after that it will go on reducing. So corresponding to that peak amplitude, whatever is the frequency, that frequency is Fn. That is the natural frequency which we are interested to find out. To know, here you see, to know this Cu, we need to know this Fnz. So that is what we are finding out by this particular response. Fnz is natural frequency of vibration of soil block system. M is mass of the block, oscillator and motor. A is area of contact of block with soil. So from the response of acceleration pickups, you can get the acceleration, that is a small az, and from there you can find out the amplitude corresponding to the different frequency Fz by using that particular expression as I showed you just now. So once you know that what exactly is the amplitude corresponding to different frequency, you can plot them for different eccentricity values. So if we concentrate on any typical amplitude versus frequency curve, then we see that first the it goes on increasing, and then once it attains a peak amplitude, then the curve start drooping down. So that frequency corresponding to the peak amplitude is called as this natural frequency of vibration of soil block system, which we want to find out. So from the test we can get this Fnz, and then subsequently we can get that Cu value. The value of Cu varies with the contact area of the base. As you have seen that the expression of Cu, area was coming, mass was coming. So all these are the factors on which this Cu value will depend on. Hence the value of Cu obtained from test needs a correction due to contact area. See, this Cu is the property of the soil, that is the spring equivalent soil spring constant. So that should be independent of this contact area. So to make it independent of the same, some corrections are to be made. What are they? That IS code recommends, that IS 4259/1992 recommends that for area larger than 10 meter square, the value obtained for an area of 10 meter square may be used. So if the area of the contact of that concrete block with the soil is more than 10 meter square, then you have to restrict that area to 10 meter square. If it is less than that, you have to use that corresponding value. But in case if it exceeds 10 meter square, you have to restrict the value to 10 meter square. Now this was all about that how you can find out the coefficient Cu using vertical vibration test. Now let us try to see that how we can get the constant using horizontal vibration test. So as the name suggests, horizontal vibration test, and as we were discussing that when the translation motion is there along x and y axis, that is along horizontal plane, then we can evaluate the coefficient of elastic uniform shear, which we were representing as C tau. So this can be determined by a horizontal vibration test. The mechanical oscillator is mounted on the block such that it generates horizontal sinusoidal vibrations in the direction of longitudinal axis of the block. In previous case we saw that we saw to it that oscillator which has been mounted on the block is generating purely vertical sinusoidal oscillation. However, in case of this horizontal vibration test, that the oscillation should be horizontal sinusoidal vibration, and that too in the direction of longitudinal axis of the block. So, we have to make sure while mounting this mechanical oscillator that it should be mounted in such a manner that it should generate only horizontal sinusoidal vibration in longitudinal axis of the block in that particular direction. So, in this case also, as it was there in case of vertical vibration test, 3 calibrated acceleration pickups are mounted on the block, one each at top, bottom and middle along the vertical central line of the transverse face of the block, so as to sense the horizontal vibration, because whatever vibration has been created using this oscillator, that has to be recorded. So, that is being done using this acceleration pickup, so that its response can further be analyzed to obtain this constant C tau. The oscillator is excited in steps starting from at rest condition. So, earlier it is at rest, there is no excited state in the oscillator, and then it is excited in steps. It is not that in one go it is excited, in steps it has to be excited. The signal from each pickup is amplified and recorded, so that we can analyze this particular data. Further, the same procedure that was used for vertical vibration test is adopted in this case also. So, once this is there, so you fix up an eccentricity setting value and then you get the value of acceleration. You find out the amplitude, you then plot amplitude versus frequency curve to know this frequency of the system. The amplitude of horizontal vibrations, that is AX, is obtained from small ax divided by 4 pi square f square, where AX is horizontal acceleration in the direction which is under consideration, because in horizontal direction it can be any, in horizontal plane there can be n number of directions. So, whatever direction that in which you want to find out the spring constant, in that particular direction you have to measure this acceleration, where f is the frequency in cycles per second, that is CPS. Then, as you did in case of vertical vibration test, in this case also the amplitude frequency plot is obtained from these observations, and the natural frequency of horizontal vibrations are determined. Exactly on the similar lines, further the amplitude of vibration at the natural frequency of the system are obtained from the pickups at the 3 locations and plotted against height of the block. So, the amplitude of vibration at, once you know the natural frequency, you can note down the amplitude of the vibration. Then you have mounted the pickups, acceleration pickups at 3 locations, that is top, middle and the bottom. So, that you can plot against the height of the block. Now, the natural frequency corresponds to the first mode or the lower natural frequency if the plot corresponds to the figure given below. So, you see, if I am plotting it with respect to height of the block, this is what is the response, this is the center of rotation, then this is top of the block, this is base of the block, where here it is in contact with the soil. So, if the condition is like that this amplitude is gone increasing here in this particular case, so the natural frequency will correspond to the first mode or the lower natural frequency. However, if the case is reverse, that is like this, center of rotation is here, this is height of the block which we are plotting the variation with, this is top of the block, and you see that the variation is in this manner. So, in this case it is the natural frequency corresponds to the second mode or the higher natural frequency if that particular plot corresponds to this particular type of figure. So, in earlier case it was the first mode. So, from that figure we also can make out that whatever natural frequency that we have obtained is corresponding to first mode or second mode, or whether it is lower natural frequency or higher natural frequency. Then, How we can find out this coefficient of elastic uniform shear of the soil? It is given by this equation, where it is 8 pi square gamma f nx square divided by a naught plus I naught plus square root of a naught plus I naught whole square minus 4 gamma a naught I naught, where gamma is defined as mm divided by mmo. What exactly are these? We will see in subsequent slides. However, this Fnx is horizontal resonant frequency of block soil system. A naught is A by M. A is, you know, area of the contact at the base with soil. M is the mass of machine, oscillator and that block. Then I naught is equal to 3.46 I by mmo. That is, mm is mass moment of inertia of the block, oscillator and motor about the horizontal axis passing through the center of gravity of block and perpendicular to the direction of vibration. Since the vibration are getting generated, the oscillator has been mounted in such a way that it is generating purely horizontal sinusoidal vibration, and that is why the whatever is the horizontal axis which is passing through the center of gravity of the block, obviously the direction of the vibration will be perpendicular to that. Then MMO is mass moment of inertia of the block, oscillator and motor about the horizontal axis passing through the center of contact area of the block and soil and perpendicular to the direction of motion. MM was the mass moment of inertia about the horizontal axis passing through the center of gravity of the block. However, this is the mass moment of inertia of block about the horizontal axis which is passing through the center of contact area of the block and soil. So, that you must keep in mind. Where this I is moment of inertia of the foundation contact area about the horizontal axis which is passing through the center of gravity of the area and perpendicular to the direction of vibrations. Now, in this case, the positive sign is used when Fnx is the second natural frequency and negative sign when Fnx is the first natural frequency. So, just now we saw that using this horizontal vibration test data, we can find out whether it is lower natural frequency or higher natural frequency, or whether it is first mode or the second one. So, once we know, then correspondingly you can assign the sign. So, positive sign for second natural frequency and negative sign for first natural frequency. Then the coefficient of elastic uniform shear C tau 1 for the actual base contact area of the foundation A1 is given by this particular equation, that is C tau 1 is equal to C tau square root of A by A1. See, A is the area of that block, but it is just modeling the foundation, it is not the exact size of the foundation. So, for that correction we need to apply. So, that is what it is. This is valid for small values of base area of foundation and may be used for areas up to 10 meter square. For areas larger than 10 meter square, the value of C tau obtained for C area to be equal to 10 meter square should be used. So, as the case was there in vertical vibration test, exactly on the similar lines, here also the area restriction of 10 meter square is there. So, in case the area of the foundation base contact area is more than 10 meter square, then you have to take that area value as 10 meter square and then go ahead with the further calculation. Then IS 5249/1992 recommends the following correlations between the elastic constants: coefficient of elastic uniform compression Cu, coefficient of elastic uniform shear C tau, coefficient of elastic non-uniform compression C phi, and the coefficient of elastic non-uniform shear C psi, as Cu is equal to 1.5 to 2 times C tau. C phi is equal to 3.46 C tau and C psi is equal to 0.75 Cu. See, many a times it is not possible to conduct, let us say, either of the tests. Maybe it is possible to conduct cyclic plate load test, but that vertical vibration test or horizontal vibration test is not possible to conduct. So what happens is that you conduct any of the tests, get at least one value of this constant, then empirical relations are available to correlate that. So let us say that if you have got the value of C tau using horizontal vibration test, then in that case, by applying this or using this particular expression, you can obtain the expression for or the value for Cu. Once you know Cu, you can find out the value of C psi, and C tau is known, so you can get the value of C phi. So these are just the correlation, empirical correlation based on the experience of different research workers and the experience of different practitioners, engineers. The relationship between Cu, C tau, C phi and C psi depends on the elastic properties of the medium, that is, in this case is soil, the size and shape of contact area and the rigidity of foundation. The values given by equations mentioned in the previous slide may be taken as average value. Since they are not being obtained from some mathematical means or some established mathematical method, they are an empirical results or empirical expressions. So that is why while you use these expression, they just give you the representative values or the average values. So today we saw that how you can analyze block foundation. We saw various aspects, that two theories are there, that linear weightless spring theory and then the theory based on theory of elasticity. Then we started with that how we can go ahead with the analysis using the first method, that is a spring method, and in that one we saw that we need to know the soil property because we are modeling the soil using the springs. So we need to precisely know that what exactly is the property of the spring, and then we saw that depending on the mode of the vibration, the property of this spring will be changing. So the question is that how we can get the property of the spring, that is equivalent spring with which we are replacing the soil. So after that we saw that how we can find out these properties. There were four type of basic constants or spring constant, equivalent spring constant, that need to be evaluated, and then we saw that how we can do using cyclic plate load test data. That after that we saw vertical vibration test and then horizontal vibration test. We saw the methodology, that how all the four this constant can be evaluated by conducting these in situ or lab tests. Then we discuss about some of the empirical relations which are available, because many times it may not be possible to conduct all type of tests. Let us say if we have the result of one type of test, then we should be able to get the rest other coefficient for spring. So we will be discussing this aspect further in the next class with the help of few examples, and then we will see what exactly is the effect of damping, etc. on the analysis of the block foundation. Thank you.
Thank you.